Hi, I'm Adam Hand with the University of Nevada, Reno. I'm going to talk about demonstration projects, related specifications, and techniques for improving density of asphalt mixtures. This is based on two tech briefs that were developed as part of a cooperative agreement with the Federal Highway Administration, and the authors are Timothy Ashtenbrenner with FHWA, Nam Tran, and Fabricio Lavia at the National Center for Asphalt Technology, and myself. As I said, this was developed as part of a cooperative agreement with FHWA. It's called the DDIAPT, or the Development and Deployment of Innovative Asphalt Paving Technologies. UNR is the prime contractor, and our partners in the agreement are Applied Research Associates and Paragon Technical Services. There's a disclaimer here that I want to read a portion of, and it is the material is disseminated under the sponsorship of the U.S. Department of Transportation in the interest of informing exchange or information exchange under the cooperative agreement I just discussed, and the government assumes no liability for the use of the information. The government doesn't endorse any products or manufacturers or some equipment you'll see, and we don't reference any standards, so there's no need to read that third part. So I said we're going to look at two tech briefs today. There were actually four that were developed, and the second set will be presented in a forthcoming webinar. So the overall objective of the demonstration projects, and actually the tech briefs also, was to demonstrate the ability to increase density through improved techniques. And those techniques might be construction practices, mixture design practices, or even specification requirements. The reason this is important is that there's a lot of literature that has shown that as we increase density, in-place density, we extend pavement service life. When we extend pavement service life, then we reduce costs associated with construction and maintenance of our network. The literature also shows that basically if you have a target density less than 92%, that density target was considered inadequate. Also, pavement service lives increase significantly or decrease significantly when densities are below 93%. And then water, basically, if we have low density, water can enter the pavement, right? And when water enters the pavement, it enters because it's permeable, and when water enters the pavement, the potential for damage is increased. And this slide just shows that the required density or reduction in air voids, might be a way of looking at it, that's needed to get the permeability to an adequate level decreases with nominal maximum aggregate sizes. So for example, a 19 millimeter mix, you gotta get the air voids down to about 6%, where with a 4.75 millimeter mix, you can have your air voids around 9%. So pretty significant difference. The demonstration project goals were to support state DOTs in a couple of things. One was evaluating their existing density requirements that they have in place for acceptance, and then to review and update as needed current field density acceptance criteria. The demonstration projects included existing practices and new materials and technologies. Associated with the projects were 29 workshops at which over 1,800 people attended. And the map here shows the states that the demonstration projects were held, or the workshops were held. As an incentive to the states to do a demonstration project, FHWA provided some money, and that was $50,000. That came along with some suggested minimum thickness for the overlays, minimum design life, as well as a minimum section length, so that there was adequate area in which to get a sense of variability associated with the pavement section density. And basically what was done is it was a control section was built, and then at least one other section that used some different technique to increase density needed to be built. More than one could be built, but at least one had to be built. And basically contractors were encouraged to use techniques that didn't add cost, significant cost. So in other words, not adding a roller, but rather adding passes with a given roller. And then the DOTs went ahead and performed their normal acceptance testing, whatever that testing method was and frequency. And it was encouraged that cores be taken and used as a basis for density, or if they at least be referenced. So there were, over a 3-year period, 26 states participated in the development and construction of 29 demonstration projects. There were 35 control sections. That's the state doing the regular thing, and then there were 86 test sections, and those were the sections where something was changed. So there were 121 test sections total, and you can see the states that participated and which year and phases 1, 2, and 3 were years. The metrics used to measure the success of the demonstration projects were listed in this table here, and one of them was to see if the density that was increased by the change that was made by greater than or equal to 1% over the control section, and that occurred in 17 of 29 demonstration projects. Another goal was to see if whether or not the test section achieved a density that was greater than 94%, and that occurred in 23 of 29 test sections. And then if you put those together, the goals were achieved in 24 out of 29 demonstration projects. Most states were using PWL, or percent within limits, as the tool, the statistic for their acceptance on density, and a handful were using lot average. And I won't go through the details of all of that. That's illustrated in this slide also. We'll come back to that in the end. And 2 states all but 2 states were using DOT data for acceptance, and 2 states were using contractor data that was validated for acceptance. Now, I'm not going to go through the details of this. I'll encourage you to look at the tech brief to find this, but essentially there's details on the states, the mixes, and all that type of stuff in the tech brief, along with the density data and some other information on sort of roadway classification and so forth. At any rate, this slide shows that this is the first 12 test sections or demonstration projects, and shows the average density that was obtained was 94.3%. The average standard deviation was 1.25%. And there's an example state added to this table when you go look at it in the tech brief. And the trick here, the unique thing about this state is their lower specification limit was 91.5. This slide shows a couple of things. We've got a lot going on here. On the secondary y-axis, we've got lower specification limit. So these states had lower specification limits of 92%. These of 92.5. These were at 93. We're back down to 92, 92.5. I'm sorry, 93, and then 92. And what's interesting here is we see that 9 of the states were able to have less than 6% of the density test results below 92% density. So that's very good, right? So this is the number that were less than 92%, and so again, there's the 6% mark, and 9 of the states were able to achieve that. The average densities ranged from 93.7 to 94.9. Now this is some data compiled from Maine DOT over the period from 2013 to 2017. The average density in Maine, their spec is working really well, is 94.5%. And they have less than 6%. They have only 5.8% below 92% density. This is a frequency distribution just like the previous one. And this is for that example state with the lower spec limit of 91.5%. The average is about 2% less than what Maine was getting at 92.6, and over 25% of the test results are below 92% of GMM. So the pretty big difference with that lower specification limit. Now this slide summarizes the data. 9 states that use PWL, or percent defective, which is essentially the same thing, with lower specification limits between 92 and 93, had a range of 3.1 to 8.4% of the density test results below 92%. 3 states use the minimum lot average with a lower limit of 92%, and they had between 5.3 and 11% of the density test results below 92%. 2 of the states that use minimum lot average also had an additional requirement, for example, like a minimum individual sublot average. All 12 DOTs use incentives for density, and they range from 1.25 to 8%. Now this slide shows a combination of things. We've got lower and upper specification limits, average density achieved, and it's the same states with the example state added. And so what we see here is that the states with the higher, the 92 or between 92 and 93% lower spec limits, they average, on average, again, you're right in this about 94% range, right? Where, again, the example state averaged 92.4, and over 40% of the density test results were actually below the average. This slide shows, again, the fact that there were lots of different specifications. So there were different lot sizes, sublots per lot, the frequency of tests within a sublot, and then the way that bulk and theoretical maximum specific gravities differed among states. So, and again, the point here is to let you know that information is all in the tech brief. So if you want to go look at the details, you can find it there. Now, the lot average density needed to achieve a PWL of 90% is what most folks focus on when they go out and build a job. And the reason for that is that most DOTs use PWL, and if you achieve a PWL of 90%, the pay factor is 1 or 100%. And so the point of this slide was to try to help folks recognize what influences PWL. And it's basically the lot average density and the standard deviation, or the variability. And that's all relative to the specification limits. So in this table, if we took we just took the lower specification limit of 92%, if you wanted to achieve a PWL of 90%, if you had the typical standard deviation that's observed on density or across all the projects, you'd have to have an average density of 93.6%. Where if you controlled your variability, you tightened things up and you were able to reduce your variability, you could get, and you got your standard deviation down to say 0.75, which was observed, you could have a lower average density by 0.6%, a little over 0.5%. And so the idea here is you either have to push your density up if you've got a larger variability, or if you reduce your variability, you don't have to get to the same effort or to the same level. It's a really important concept, and it's illustrated graphically here also. And the idea here is we were just trying to communicate in the tech brief sort of how to get to where you want to be, because everybody wants to get there. The state wants the high density, and the contractor wants a high density to get good payment. So, understanding this can help both get their goals reached. So, summary of information relative to specs, to considerations for specification changes based on the first tech brief is one is encouraging a minimum of 5 sublots per lot to balance buyer and seller risk. 10 would be better, but if you have more frequent sublots, maybe 5 is okay. Improving pavement performance by minimizing density tests below 92%. And then 12 state density specifications illustrated that getting 92% or using the 92% threshold was effective, and you could end up with a small amount of test results below that. And then finally, the last concept we just looked at was that understanding how lot average density and variability impact PWL is important to the success of both the agency and the contract. The second tech brief was focused on basically the techniques that could be used or were used in the demonstration projects to try to get higher density. And so contractors made 4 different types of changes, and they were basically operational or equipment changes. Increasing the amount of effort, using a windrow elevator versus an MTV, using a conventional sprayer or conventional paver versus a spray paver, and then roller type and position. And that'll make a little more sense when we look at it. This slide shows that with additional passes or effort, compactive effort, additional density was observed. And on this for the demonstration projects, a pass is defined as the roller going over one point on the mat one time. Okay, so 1 pass, 2 passes. Now, 9 out of 28 states used less than 15 passes. 9 out of 28 also used between 15 and 20 passes. And then 10 out of 28 states used over 20 passes. There were additional passes used on 13 of the 26 demonstration projects. Now you might be looking at this data and questioning what I just said. Now, so in some cases the density really didn't change, or it even dropped a little bit in one. Well, that could be possible for a handful of reasons. One is if the density is already very high and you keep adding passes, it may not change, right? Or you may begin to break them back down a little bit. Another is maybe the mixes were low in AC, and maybe they hit a refusal density, right? Good aggregates, they just lock up and they don't go any further. And then another potential would be, especially at the real high number of passes, because it took additional time to apply those passes, the mat could be cooling, and as the mat cooled and the mix stiffened, no additional gain may have been realized. So those are potential reasons explaining those. Now, this slide really highlights a couple of things. Most importantly is that using rollers and echelon was very effective. On 9 out of 10 projects that was or sections that was done on, greater than 94% density was achieved. And it's interesting, in some cases pneumatics helped improve density, and in some cases they didn't make a noticeable difference. Okay, on one project, a windrow elevator or pickup machine and an MTV were both used. And on that particular project, the section built with the MTV had 2.6% higher density than the section built with the windrow elevator. On one demonstration project, 4 experimental sections were paved, and on those 4 experimental sections, both a conventional and spray paver were used. So the density that was observed, or the difference in density that was observed between the conventional and spray paver, was about 0.5%, and it was actually higher with the conventional paver. Now, the agencies could also make changes, right? So DOTs could say, hey, we want to try to change something to increase density, and the things that they changed were the thickness, or the nominal thickness to nominal maximum aggregate size ratio. They used Warmick technologies, or they changed the mix design in one form or another. And if we start with the thickness to nominal maximum aggregate size ratio, basically 20 states used 12.5 millimeter or half-inch mixes, 8 used 9.5 millimeter, and 6 used 19 millimeter. 2 states had thickness to nominal maximum aggregate size ratios of less than 3. 5 had the ratios greater than 5, but the bulk of the states, 20, had ratios between 4 and 5, and if you add these 6 in there, 26 had ratios between 3 and 5. This slide shows that on 4 demonstration projects compared density with adjustments to thickness, nominal maximum aggregate size, and we got increases in density, right, with increase in the ratio. Okay, yeah, that was 4 projects. On 16 projects, asphalt content was changed. So there were 16 sections on 12 projects. Asphalt content was changed, and essentially it was increased. Okay, the method that was used to determine the increase was on 3 of them engineering judgment. 6 of them used optimum asphalt selected at a reduced design air void level. 3 selected an optimum asphalt content selected at a reduced number of gyrations in gyratory compactor. 1 adjusted the optimum to account for aged binder not being effective in the mix, essentially requiring higher effective binder. And then 7 selected optimum asphalt contents with supporting information from performance tests. This slide shows that with increased asphalt content, an increase in density was observed. 7 of 11 projects had increases of greater than 1%. 8 of 11 had density increases above 94%. And 8 of 11 either had, again, the increase of greater than 1% or the increase of greater than 94%. Remember, that's going back to our goals on the were the project successful, or the changes. 5 demonstration projects integrated warm mix technologies, 2 at reduced temperatures and 5 at normal temperatures. Projects that used the warm mix at the reduced temperature or warming temperatures were able to achieve equal density with constant roller passes. So in other words, they did not have to increase density or roller passes to get their required density. Projects that used warm mix at normal production temperatures were able to achieve higher density at the same or the same density with less passes, in some cases there was no increase in density. The projects with no increase in density, though, had densities that were already at 94%. Now, 24 or 26 states made changes, are in the process of making changes to their specifications, and I won't go through all of them here because I'll run through them in sort of in groups by grouping of states. So 3 states made changes to their primary density specifications. Okay. And some states will have a spec where for high volume roads you've got a criteria that's here, and then when we go to lower traffic categories, you might have a lower specification requirement. We call those tiered specs, right? Well, so 3 states that had tiered criteria were included, and they're basically changing the criteria within their tiers. Okay, and 1 state improved its secondary density specification. So again, changes to push density up. 5 states made changes to their quality measures. 3 states went to PWL. 1 state using minimum max lot average is adding a minimum sublot average, and 1 state is implementing average absolute deviation with an increased minimum. 14 states changed their upper or lower specification limits. 5 of them increased their upper limits to between 97 and 100%. 10 increased their lower specification limits, and specification limits are typically being increased to 92% if they're using PWL, and 93% if the agency's using lot average. 2 states that are using lot average are adjusted lot and sublot sizes, and again, the intent there is to increase sublots reduce risk for both the contractor, the buyer, and the seller, so the agency and the contractor. Although 10 is encouraged, 10 sublots is encouraged. Many states do have frequent smaller lots with fewer sublots. So summaries of states adjusting incentives and disincentives. Basically 7 states did that. So they changed the incentives associated with their density acceptance quality characteristic. One of them increased it by 150%. One state added voids and mineral aggregate, or VMA, as an acceptance quality characteristic to the composite pay factor for hot mix, and that was done in as a method to try to increase the minimum asphalt content in the mix. 2 states identified the need to make changes to their inspection validation processes, and in one state, aggregates used in the mix design and aggregates used in the field production were different, and that was identified. So they're going to work on their aggregate verification in production. And in one state that used contractor's test results for acceptance, with 5 passes of a single roller, the contractor's test results indicated densities of over 92%. Cores tested by an independent third party indicated the density was around 89%, so the state's going to strengthen its validation process. This is a really interesting observation, and it's from a contractor, and basically that improving contractors' quality control, or really their crushing and feeding of their aggregates, led to reduced standard deviation in density. So the density standard deviation went from 1.4 to 1.0 by improving the consistency of their aggregates. 3 states are looking at changes associated with thickness and nominal maximum aggregate size, and basically one state saw the benefit, but because they're using thin overlays, they're looking at going to smaller nominal maximum aggregate size mixes, so 9.5 millimeter nominal maximum size mixes. In one state that does a lot of late season or cold weather paving is considering changing the minimum lift thickness from 1.5 inches to 2 inches, because the mix cools at a slower rate as you increase the thickness of the mat. 4 states added longitudinal joint specifications or increased the lower joint specification limits, and that comes up in the next webinar in much more detail. So with that, one other thing that was done is that 2 states made changes to their testing and calculation. One is measuring density using a nuclear gauge, and moving forward, they went to cores, correlating it to cores, and one went to using theoretical maximum specific gravity as a reference for in-place density. The 14 states looked at increasing asphalt content, and again, the techniques that were discussed earlier are the techniques used: regressing air voids, reducing the number of gyrations, or accounting for the aged binder in the wrap. And 10 states are looking at the use of performance tests, and this is great because they don't feel like volumetrics alone is sufficient, which is consistent with all the movement towards a balanced mix design. And on these projects, 10 states used a rutting test, 8 states used rutting and cracking tests, and they had several states had already begun to use those tests prior to the demonstration projects. The last item is intelligent construction technologies, and 4 states are implemented intelligent compaction, and that would be the mapping portion, not the stiffness numbers. 3 states are implementing thermal profiling. 2 states are implementing density profiling systems. 1 state's pairing up the intelligent compaction mapping with the thermal profiling, and 1 is marrying up the thermal profiling with the density profiling system. In summary, observations from the demonstration projects associated with achieving higher density are summarized here. Basically, if you got a sound mix, with an adequate amount of asphalt in it. Achieving higher density is possible without extraordinary effort. Using breakdown and intermediate pneumatic rollers and echelon was shown to be very effective. In general, density increased with compactive effort. And the trend for states is to use smaller nominal size mixes. Again, many folks are looking at going to 9.5 millimeter mixes. And then, of course, many states have either made or plan to make density specification changes. With that, I'll encourage you to go to the website listed here. You can find the two tech briefs, HIF 21-021 and HIF 21-022. And of course, you're welcome to reach out to myself or Tim Ashton-Brenner with FHWA if you have questions. Our emails and phone numbers are there. With that, well, thank you for joining us today.